This talk is going to be about Twirling and Hamiltonian engineering for GKP quantum computing. So now you have, I believe you have 25 minutes.
Okay.
Yes.
Yeah, thank you for this introduction, and thanks to the organizers for once again putting together this very nice conference. Right. So this talk is going to be a rather technical talk where I outline the key technical steps in my construction. For that, I'll discuss some different notions of twirling, how they relate to each other. I'll introduce an energy-constrained twirl for GKP, which I believe to be fairly powerful. And finally, I will show how we can use these techniques to engineer a GKP stabilizer Hamiltonian via something that is known as dynamical decoupling. So to jump right in, the central object that matters when talking about a twirl is something that is called a group projector, which I outlined here, which is simply a function that maps an operator or that maps an input to something that commutes with each element of some group G here, right? So the simplest physical realization of this group projector is also the first one of the first papers where this notion of a twirl appears in this Bennett et al. Paper, where the idea is simply to, here we take some 2-qubit state and we apply some random U tensor U rotations to the state. If we do this and average over all the different unitaries that we can pick, what comes out is a state that will effectively be diagonal in the Bell basis, right? So if we have some input state that inherently has some entanglement, the output state will be a better entangled state, right? So this is what I refer here as a state twirl. And very similarly, something that most people are a bit more familiar with is something that is called, so let's put this away, the channel twirl. In a channel twirl, you essentially apply the same group projector, but now you apply it to the matrix representation of a channel which acts on some supervectors, right? So as an example, if I have some channel that I can write in this form, right? I have some cross operator, tensor cross operator conjugated, and I apply a twirl, say T is a Pauli group, and I apply a twirl with group elements that look like Pauli tensor Pauli conjugated, then what comes out will effectively be a channel that has only operators that commute with Paulis up to a phase. Ergo, we will get an effective Pauli channel. So this is a very neat trick that you can also implement in actual channels in order to kill off coherent errors, for instance. So, and finally, the third important notion of a twirl is what I call here a Hamiltonian twirl, right? We twirl a Hamiltonian. This is done by a technique known as dynamic decoupling. And I think it's most easy outlined in this example here. So here, as an example, I have some Hamiltonian, you see as a unitary evolution of some Hamiltonian, where I have some Z rotations that I don't like, that I want to get rid of. So the trick is to interleave this Hamiltonian evolution in a smart way with some X pulses. And if you average over well-chosen time bins, then the effective Hamiltonian will be a Hamiltonian where this extra Z rotation is effectively twirled away. It's projected out because it doesn't commute with the X gate. Right. So these are the different shades of twirl. And now we know that once we have come up with one of these twirls, it's actually fairly easy to translate it into the other incarnations of twirling. Right. Okay. So ultimately, I want to talk about GKP. And the most central object of GKP codes are the displacement operators. Right. So here we have the stabilizers, which are displacements of this amplitude. We have the logical operators, which are the displacements of half the amplitude. And these displacement operators are particularly nice because I here consider them to be easy to implement in practice. A nice feature of displacement, which is very closely related to the structure of these operators here, is that they commute just up to this phase given by this symplectic 2 form up here. And finally, a nice feature of these displacements is that they form a complete operator basis for operators that act on bosonic Hilbert spaces. So due to this, any operators that we have, we can write in this form with some displacement acting to the left, to the right, and some factor weighing, putting a weight on these contributions. This factor here will be very useful for us, and I call it the chi function, analogous to the chi matrix when you look at the Pauli basis for qubit channels. So essentially, since in GKP, what we care about are displacements, the support of this chi function is crucial as it determines what displacements are involved in certain realizations of channels. Okay, so now that we want to come up with a twirl for GKP error correction, the most natural thing to do is to twirl a GKP channel using displacements. The idea here is that, okay, we take some displacement amplitude which we sample from a probability distribution mu. We apply displacements corresponding to this amplitude to some state prior to sending the state through the channel, and after the channel evolution, we apply the reverse operation and undo the displacement. What is nice here is that if we represent this channel using this chi function representation, then we see that the chi function transforms with a factor that is given by the Fourier transform, by the symplectic Fourier transform of this probability distribution here. And we can actually repeat the step, right? We can repeat this application of the super operator that the twirl is, and by that increase the power on this function here. So all of this is not new. This was this trick, I mean, not this trick, but the trick of the twirl was already used in several papers. Especially it was used in order to render channels effectively displacement diagonal, which is nice for simulations, but has the drawback that if you wanted to actually implement it in practice, that this probability measure would be not normalizable and you would need to implement really, really big displacements. So my goal here is to come up with a twirl that you can actually do, right? That you can actually implement an experiment, maybe to pull off some coherences. So the central twirl, so the central component of the twirl that I consider here is by choosing the right probability distribution. So what I'm showing here is a lattice that labels the different displacements that I do. Here I consider logical displacements here, of this type, where n and m just label the vertices on this graph here. So my probability measure over displacements looks like the following. With a quarter probability, I don't do anything. With an eighth probability, I apply the x, z, x dagger, z dagger gate, because these are different things when you look at the full Hilbert space. And with a 16th probability, I implement the different incarnations of the y gate in GKP. Right. So if you use this probability distribution, this is a straightforward calculation. This factor that comes in from the twirl will look something like this. So because of the Fourier transform property of the structure of the factor, we can see that a local probability distribution can actually lead to some non-local terms. And by the way that I chose this probability distribution here, I'm going to have this approximate projector onto stabilizer displacement amplitudes. Right? So here I draw a picture of this factor. If I only apply the twirl once, I'm going to see that all the off-diagonal elements that correspond to some stabilizers will not be affected, but all the components, all the off-diagonal channel elements that don't correspond to any stabilizers will be dampened. And as I increase this twirling level, and here it will be damped further and further and finally projected away. So effectively, using this trick, we can obtain a channel that only allows stabilizer shifts as off-diagonal contributions. Okay, so, well, I mean, so this thing with the n is a very nice trick, but certainly in experiments, you don't really want to repeat this twirl over and over again. what I show on this slide is that you also don't need to, because effectively, one thing you can do is you can interpret the single step twirl as a single step of a random walk, right? Where your random walk happens on the displacement lattice. And if you have multiple of these twirls, then you can simply combine the displacements and look at the probability amplitudes for the accumulated displacement amplitudes. This is something that you can compute, and we have this closed form such that if you wanted to actually implement this, only a single shot twirl would be necessary. So it turns out that this n parameters, this twirling level here, can be seen as a form of regularization of a twirl. You can increase the n, go to infinity, and in the end up again at a perfect infinite twirl, which then will also be a exact projector. So, right, I didn't write this here, but a very nice application is a very nice other application would be to not consider logical displacements as in corresponds to these edges here, but instead to consider displacements that are composite of stabilizers, right? By that, what would happen is that you would allow for logical coherences, right? But everything else that is not a logical coherence would be killed off. So that's right. So that would be a different way that you could protect channels using this twirling method. Okay, so yeah, so this is the part about twirling. And finally, I want to come to this technique of twirling Hamiltonians. So to twirl a Hamiltonian, let's look at a Hamiltonian that has some base part, right? So this is a static Hamiltonian, and I'm going to modulate this system using a time periodic control Hamiltonian with some periodicity Tc. So since this Hamiltonian is time periodic, when I look at the system, the central part that matters about the system evolution is this unitary evolution over a single bin of this periodic evolution. Now I take the single bin of the periodic evolution and I structure this control Hamiltonian such that it realizes a certain pulse sequence which interleaves with the natural Hamiltonian evolution given by the base Hamiltonian, which I also will later refer to as the substrate Hamiltonian here. So if we do this, and if we choose the time binding small enough, then what one can compute is that the Hamiltonian evolution over this time bin will be approximately given by the average Hamiltonian in this time bin, which one can once again translate into a form that looks like this here, which looks extremely close to this kind of group projector that we've seen earlier. So now we have some extra weighing factor, tau k, which represents the relative length, the relative time length of these time bins, and these qk's are these accumulated pulses, up to the time step k, right? So there's some normalization condition, and we can also do the reverse and get the pulses from the qk's, right? So yeah, so in summary, what I want to show on this slide is that the first order average Hamiltonian under this construction corresponds to a certain twirled Hamiltonian. So yeah, so I want to apply this twirl to a Hamiltonian. For that, let us first consider the characteristic function of a Hamiltonian. I can write a Hamiltonian in the displacement basis, where this h naught here represents the characteristic function of the Hamiltonian. And if I straightforwardly apply this dynamical decoupling sequence that I've come up with earlier, so I'm going to associate these relative time lengths with the probability distribution that I've shown. I'm going to associate the accumulated pulses with the displacement operators that I've shown earlier. Then what happens to the characteristic function of the Hamiltonian is that it will effectively be mapped onto the approximately projected version of this characteristic function. And here in this projection, you once again see that by the way that we have chosen this twirl measure, we're going to have this cosine function, which gives a periodic projection in phase space. Sorry, in phase space. Okay, so similar as earlier, we can also by by changing this factor of n here, we can also increase or decrease the strength of this projection as we please. So this is a means to approximately project a Hamiltonian onto stabilizer displacement in its support. So in order to construct a GKP Hamiltonian, in order to construct a GKP stabilizer Hamiltonian, which has this structure, what we would need is a Hamiltonian that's what we would need is simply a base Hamiltonian that has support on these GKP contributions. If we look down here in the blue circles, I represent all of these regions that are not filtered out by this dynamic decoupling sequence. And so effectively what we want to target is to have a Hamiltonian that is supported on these 4 dots. These 4 dots here in this picture represent the characteristic function of the GKP Hamiltonian. Yeah. So ultimately all we need is actually to find a Hamiltonian that has support on these 4 dots here. So when I was looking at this, I was trying to figure out what kind of system would approve this. So the easiest, the most straightforward choice to pick here would be, for instance, to choose a base Hamiltonian that has a constant characteristic function. That is, the Hamiltonian is simply a continuous superposition of all displacements. Alessandro, who's going to talk next, pointed out to me that this Hamiltonian actually exists, and it actually corresponds to the parity operator. Well, this thing is nice. This works in simulation, but I wouldn't know of any implementation of such an operator, so I had to keep looking. So the nice thing about the parity operator is that it actually looks fairly close to the stabilizers, or it's exactly the stabilizers of cat codes, for instance. So I started to dig into the cat code literature and found the closest best thing, which is a Hamiltonian similar to the one outlined in this Cohen et al. Paper that is given by an LC oscillator in parallel to a solution junction. So let me try to explain the intuition between the circuit and its characteristic function. So the Josephson junction has a Hamiltonian characteristic function, which is given by 2 dots up here and down here on the imaginary line, where the radius or the distance of these dots, of these deltas to the center point at phase space, is given by the impedance of this LC circuit here. So if I go into the rotating frame of the circuit, what's going to start to happen is that these dots are going to start to rotate in a circle. Right? As I increase the cavity frequency, these dots rotate faster and faster and faster, such that finally, if I apply the rotating wave approximation, this fast rotation will simply become completely blurred out, and all I'm going to see of the Hamiltonian is this circle, right? So now I have found a Hamiltonian that actually has support on these stabilizer displacements, so all I need to do is to tune the impedance of the circuit such that the radius actually corresponds to these square root 2 pi amplitudes. Okay, so this is essentially the trick. I have done that, and so such that effectively, I could do some numerics on this. So what I do is I consider the circuit that I've seen earlier. I apply the rotating wave approximation. I apply the dynamic decoupling sequence and obtain a Hamiltonian whose properties are outlined here. So the two lowest energy eigenstates, as you can see here on the left side, are given by GKP H plus and minus states, right? So effectively, yeah, two H plus and minus states, and by increasing this twirling level, I'm increasing the sharpness of the peaks of these H plus and minus states. Right. Here on the right side, up here, I plot the effective squeezing parameter as it goes down with the twirling level, and here and down here, what I'm plotting are the 10 lowest eigenenergies of the effective Hamiltonian, where the lowest two energies, which correspond to the plots as seen on the left side here, are marked in red, and everything above is marked in blue. So what you can see here is that the Hamiltonian, the effective Hamiltonian that is constructed in this way is even gapped, with a gap that shrinks as you increase the Twirling level n and makes the effective Hamiltonian get closer and closer to the actual exact GKP Hamiltonian. This effect of a gap due to an approximation is something that is also very similarly observed in this Rimmers et al. Paper that Alessandro is going to talk about next. Right, so let me show how I'm doing on time. Very good.
You have 5 more minutes.
Okay, perfect. I'm almost done. So to summarize, I have introduced a regularized finite energy channel state and Hamiltonian twirl that already has an effect for fairly small displacements. So this I hope to be practical for experiments. And I have applied a dynamic decoupling sequence to a chosen substrate Hamiltonian in order to realize a GKP stabilizer Hamiltonian. I should note, I didn't write this here, that this technique is very similar to what people look at in terms of Floquet engineering, right? Yeah, for those who know what that is. So the drawbacks of my protocol and some things that I hope to be able to improve on in the future is that this dynamic decoupling protocol is still constructed in the bang-bang limit. That is, in the constructions that I've just presented, I have chosen instantaneous displacement pulses. And in order for this whole approximation to work out, I would need very, very fast displacements below 1 nanosecond for the given implementation for all of this to work out. So a natural next question to ask would be whether we can achieve the same effect using a continuous drive. Right. Furthermore, one can, I'm planning to expand a bit on these twirling techniques and try to assemble effective twirls out of smaller building blocks of twirls. And very finally, a question that I've also been talking to Alessandro about is to more rigorously characterize in what sense one can actually speak of self-correction or passive error correction for GKP once such a GKP stabilizer Hamiltonian is realized. So if you want to learn more about this talk or about the things I've just presented, you can check out the paper online, which is also appended with much more discussions as I've presented here. And yeah, and I think this would even be it. I'm happy to take questions.
Thank you, Jonathan. So, so we don't have. So we have one question for now. So your parameter regime, it's from the organizers. I don't know. I think your parameter regime implies that the gap will be pretty small for typical parameters, say gigahertz frequencies for DLC. However, right. Since this is in the rotating frame, I'm not sure how to think about it. Should we be worried about heating or diabatic errors in an adiabatic Floquet state preparation, where the drive terms are gradually ramped up? Perhaps.
Well, I mean, ultimately, the system will die of heat death, right? So the regime where this Floquet Hamiltonian has some thermodynamic meaning is only going to be a finite. It's only going to be on a finite timescale. But as you reduce this t parameter, the period of the control, this timescale gets exponentially longer and longer. So I'm not sure I answered the question. So the parameter regime
yeah, go on.
Yes.
Sorry.
No, I'm just saying there's a parameter regime indeed. So for current devices, the parameter regime indeed is fairly limited. So I've done some sample calculations with like a 5 gigahertz cavity, where of course I had this maybe unreasonable assumption that I can tune this to an impedance of twice impedance quantum. Resistance quantum. And in this regime, I would have like a time binning of this capital T in the microsecond regime, right? So if the range where my Hamiltonian has a thermodynamic meaning is exponentially long, in the inverse of this time scale, then I hope that this could be enough to at least see some effects in the lab. I should note that a similar, I mean, not this implementation, but this driving-induced GKP Hamiltonian has also been investigated independently numerically in a paper by Liang et al., where they do see the peak structure and so emerging.
So I guess Arne, if you wanted, I don't know whether this is you, Arne, who had asked the question. If you had any follow-up comments on it, you can, I guess, jump in. Question. Otherwise, it was a little bit fast for me, so I didn't completely understand. This part about the dynamical decoupling. So you mentioned you're going to switch between two Hamiltonians, HC and HC, so I guess this here you have only this rotating frame. That's what replaced all this thing. Is that what you're? How to understand this? So in this H0 and HC of T, so you want to engineer, for example, the Hamiltonian of the GKP that you mentioned. So what is your H0? I understood that this is the whole thing is basically, I guess, this Hamiltonian of the circuit, which is rotating. It's just one HC of T, right? There is no H0, if I understand correctly.
Yeah, exactly. So this H0 is going to be, yeah, I could have been more precise. This H0 is the circuit that I've presented already in with the rotating wave approximation already applied to it. So there's the natural constraint that this rotating frame, this rotation induced by the cavity frequency needs to be really, really large, such that this HC actually sees only sees this evolution.
And so yeah, also another question is about it's myself. It's don't you worry about this second order terms? So I guess the second order terms in this they're gonna come in perhaps and limit. Yes.
Right. Yeah. So second order terms are in the way that I've presented here are going to come in, even though they get smaller when I gets smaller when I reduce the team. I mean, if you imagine that there's like some generic circuit parameters that I've chosen, this T is in the 10⁻⁶ regime. This T squared part will be fairly small. Furthermore, they are actually more advanced dynamic decoupling. So this is just intended to be something of a first step. There are more advanced dynamic decoupling techniques. For instance, I could, by choosing the ordering of the pulses accordingly, I could actually kill off the second order term.
But what is this TC here? Is this TC just in your case it's going to be some detuning of the, in your case, it's going to be a detune. In your rotating wave approximation, is it just the frequency of the mode?
TC is a period of the drive, right? So I'm going to drive it. So you imagine this. If I take the global time evolution of the system, I'm just going to bin it into bins that are TC long, and every bin I'm going to modulate with I'm going to interleave with these displacements.
Yeah, but my question is about the particular, the next page, maybe the next slide that you have. So, I'm sorry, I'm talking about
this one.
This one. So for this case, I guess. So what is, if I understood correctly, there is no. What's the control here? There is no.
The control. Yeah, on this slide, the only place where you can see the control are the blue circles. I mean, I'm not showing any control here. This slide only concerns this H0 Hamiltonian that I've shown on the previous page. I'm only trying to look for a suitable substrate Hamiltonian that I can filter.
I see. Oh, I guess I'll need to read more thoroughly your paper.
Yeah, I'm happy to discuss more, more later.
Okay, thank you very much, Jonathan. So I guess we can stop here. Everybody else, you can ask more questions.